For the final project of Dr. Bhatia's Fall of 2023 Vehicle Dynamics course, our group studied the motion dynamics of the same car from our mid-semester project, a 1999 Mazda Miata. We analyzed the Miata's ride, bounce, pitch, and roll dynamics.
There we go. Reliant Robin.
This video will showcase the results of our investigation into the motion of the car.
For the experimental portion of the project, 2 experiments were conducted. The first was a simple experiment of the deformation of the suspension system when a known mass was applied across the front and rear axles. To do this, one group member measured the static height from the ground to the bottom of the edge of the wheel well. Then, another group mate with a mass of 72 kilograms sat on the hood, and the measurement was taken again. This was also done with the rear end of the car. By taking the difference of the static and deformed heights, a displacement can be determined to calculate ride rates. The second experiment was a bounce test of the front and rear suspensions. This involved one group member repeatedly pushing down on one end of the car while trying to match the rhythm of the dampened suspension. After 5 seconds passed, the number of bounces was recorded for the next 15 seconds. By taking the bounces over the elapsed time, a natural frequency can be experimentally determined.
To find the static stability factor, we took the average track length divided by 2 times the height of the center of gravity and found the value to be 1.6. Our estimated rollover threshold was calculated using the equation the square root of 2 times gravity times the square root of the track divided by 2 squared plus the height of the center of gravity squared minus the height of the center of gravity, where the track length is the average track between the 2 axles, and the center of gravity came from the Miata's information and gave us the result of 2.79 meters per second, or 6.242 miles per hour. To calculate the ride rates, we needed a known weight to be put over each of the 4 tires and the average change in the height over each axle due to the applied weight. From the measurements, we found the average change in the front axle was 0.0135 meters and the rear axle was 0.0254 meters. Using these changes in height and the equation of weight applied divided by 2 times gravity divided by the average change in the height in the front or the back, we found the front ride rate to be 26,381.06 Newton per meter, or 150.64 pounds per inch, and the rear ride rate to be 14,014.94 Newton per meter, or 80.03 pounds per inch. Using the calculated ride rates, we estimated the roll stiffness in each axle using the equation 1/2 times the ride rate times the average track squared. Combining the front and rear roll stiffness values gave us 41,200 Newton per meter per radian. To find the roll distribution over the front and rear axle, we used the equation 1 divided by the track length times the height of the center of gravity times roll stiffness, all divided by the total roll stiffness. The distribution of the roll stiffness to the front axle is 0.2 per G, or 65.59%, and to the back axle is 0.11 per G, or 34.41%. The roll gradient was found using the equation mass times gravity times the height of the center of gravity minus the height of the roll center divided by the total roll stiffness of the car. We assume that the roll center is 0 meters due to the AA arm suspension in our vehicle, giving us a value of 0.12162 radians per G, or 6.969 degree per G.
In order to find the front and rear natural frequencies, we utilize the ride rates found earlier. By taking the square root of the ride rate over half the rear weight times 1/2 pi, we were able to calculate the natural frequency of the front axle to be roughly 1.52 Hz and the rear axle to be 1.11 Hz. When comparing these results to the natural frequencies experimentally recorded, you can see that both calculations were very close to the measured values. The discrepancies between the values can be attributed to the shocks. This car has two anti-roll bars, with the rear anti-roll bar being stiffer than the front. The roll stiffness distribution for the front is about 65% compared to the weight distribution of 50-50. Ideally, the roll stiffness distribution should be 5% greater than the weight distribution, so the anti-roll bar should be made thicker in order to ensure safe handling.
Our Miata's suspension type is a double A-arm in both the front and the rear, otherwise known as a double wishbone suspension. This suspension type has some of the best ride comfort, handling, and safety metrics among all other suspension types. The cost of parts and assembly continues to set this more delicate suspension apart from others, with it also having one of the largest requirements for space inside the chassis of a car. This concludes our final project for Dr. Bhatia's Fall of 2023 Automotive Vehicle Dynamics class. Thank you for watching.